And welcome back, AP Calc students. Time for more FRQs, free response questions from old AP exams. Today we are looking at the year 2014, question number 3. And you very quickly surmise by looking at this one, we have a derivative graph. And we're going to have to pick through it and probably do a little geometry, a little fundamental theorem, and figure out some maxes and mins, that type of thing. So let's see what we've got here, and then maybe we can review some derivative graphs, and then we'll continue. So, let's see what we have here. It says the function f is defined on the closed interval -5 to 4. The graph of f consists of 3 line segments and is shown in the figure. Let g be the function defined by g of x is equal to the integral from -3 to x of f of t dt. Okay, now there's a couple things right away here that make this just a little bit unusual, and here's what it is. First off, I want to show you that they say this is the graph of f, and want to show you this, just some old notes here. If I were to give you the graph of f prime and have you do the fundamental theorem, for example, you know that the integral there would equal the f of b minus f of a. Okay? And if I were to ask you to solve for one of these two, and actually we do this a lot in questions, if I said I want to figure out what f of b is, you would add f of a to the other side. In fact, we frequently say things like, don't forget to add your initial condition to your integral. Sometimes we're manipulating the fundamental theorem to get these values. Okay? And this is not unusual. We kind of move these around. Well, what makes this question a little bit odd is that they're defining a new function where the inside is the derivative, but we don't need to do this extra piece, and so it almost looks incomplete, but it's not. It's just the nature of the way this one is, and it actually implies that the initial condition is 0. So here's what I mean. If you will notice, on the original question gives us, it says g of x is equal to the integral from -3 to x of f of t dt. Now they're purposely mixing up the letters to just try to give you something to be confused about. So what I'm going to do is I'm going to take this g of x and I'm going to put it over here and take it off the front, and I want you to compare this to this. So you know that the relationship of what you get after integrating, if you take the derivative of the function used, you're going to get the function that was in the integral, which is why we call this the antiderivative sometimes. So what's in the integral is always the derivative of the result of integrating. It's always a check we do. Well, that's true here for this question too, but they decided to change the letters. So if what's in this integral is the derivative of the result, then instead of f, we actually could call this g prime. So I'm going to, with my finger, erase f here, and I'm going to call this g prime, because that's actually what it is. It's g prime. So why did they call it f? Because it's an AP test, and they're trying to make it hard. So f is the same thing as, and I'm going to go up here on my graph here, and I'm just going to write that it's g prime. They're the same thing. It's the graph of g's derivative, which is f. So that's the first thing that's a little bit curious. That's not that big a deal, but this next part is, if you would now that you see that it's g, well, the integral of g, if I do the fundamental theorem, you would say, oh, well, that's going to be g of x, and don't I need this other part here, g of -3? Well, I'm going to now rewrite the question again. It looks like it's incomplete, because the question is defined as g of x is equal to the integral from -3 to x of, instead of f, I'm going to put g prime of t dt. And if you'll notice, they give you this, but it kind of looks like, you're like, well, where's the g of -3 part? Well, the fact that they don't have it here, it could be just the way they want to define it, or it could imply that g of -3 was 0. But regardless, it's not there. So what you don't want to have happen on the very first question on here is you don't want, part A is what I mean, when you see part A, I don't want you to be locked in that automatically whenever you have one of these questions, you need to have the integral, f of A and f of B both need to be present. Sometimes they're not. So just keep that in mind. They can define an integral any way they want, but in reality, it meant this was probably 0. That's why it wasn't on there. Okay? So that's one little thing on here. So I want to go to part A, because that'll tie in real nicely here. So if we look at part A says to just find g of 3. And it's actually a really easy question. So if g of x is equal to the integral from -3 to x of f of t dt, they just want you to find g of 3. Well, I'm just going to put in g of 3, and I'm going to integrate from -3 to 3 of f of t dt, which means it's a geometry question. So I already have the -3 there, so I'm going to go to the graph. I'm going to say, well, I'm going to go from -3 to +3. Well, I have this big triangle right here, from -3 to +2, and then I have this little guy right here. So I've got this little triangle here, and then I've got this big one up here. So if I just know my geometry formulas, I could figure out the big triangle. So let's do the big triangle. So I'm going to say, well, the area of the, I'm just going to put B with a triangle next to it, is equal to 1/2. The base of this one, we're going from -3 to +2, so that's going to be 5. 1/2 5, and then the height is 4. So half of 20 is equal to 10. So it looks like this 10 is the area of that triangle. And then this little guy right here, that's 1, obviously. And then I have to figure out this length. Well, sometimes they like to mess with you here. The slope of this side right here, if you notice here, you went over 2 and all the way down to 4. The slope of this line is -2. I'm actually going to write that right here. The slope of that line is -2. So every time you go over 1, you go down 2. So from 2 to 3, from 0 I went down 2, so this point right here, that coordinate right there had to have been 3, -2. So this distance is 2, this is 1, so for the little triangle, we'll do that. So the area of, I'm going to say the small triangle, is equal to 1/2, its base is 1, and its height here is, I'm going to put a -2, because we are below the x-axis, so this is going to equal -1. Okay, so this little guy here, this area here is -1. I'll circle that. Okay, so this thing right here, doing all the geometry work over there, it looked like I got a 10 for the top there, and then I subtracted the 1, and it looks like my answer is 9. Okay, and so that was just substituting in the value, but I took a little time here to explain this because some students get confused because they're like, where's the rest? Isn't there a piece missing here? This is incomplete, and it's not. It just was defined that way. Okay, let's move on to part B. Part B says, on what open intervals containing -x from -5 to 4 is the graph both increasing and concave down? Well, now I'm going to erase this, and I want to do our derivative, our function and derivative graph review. Very important, and I'll try to sneak these in over here. You want to have this memorized and down as good as you can. So there is my function, f, and here's the x-axis here, and I'm going to graph the derivatives. So derivatives in red. If you remember, wherever I have peaks, valleys, or flat spots, I have handcuffs. And so I'm going to handcuff this to the x-axis because I know that my derivative is going to go through the x-axis right there, because the slope of the tangent is 0, the graph of the derivative has got to be 0. Slope of the tangent is 0, graph of the derivative is 0. So the original function is increasing, means the graph of the derivative is positive. Original function is decreasing, graph of the derivative is negative, but back to 0. And the graph of the derivative is increasing, I'm going up. So there's the graph of f prime. Now, you may have been wondering, why is this red? It's red for that reason. So I overlapped this before we started with red to show that this is a derivative graph, and that's what we're going to be reading, because it's actually g prime. Okay, and now we'll move on and do the second derivative. When you do the second derivative, you treat the first derivative like an original function and just handcuff its peaks and valleys. There's only one right here. And when the derivative, or the red function, is decreasing, the graph of the derivative's got to be negative, but then it's going to hit 0. The red function is increasing. We're going to here. There's your second derivative. And where your second derivative hits 0, that's going to give you your, right there, your inflection points. Okay. All right, so we got that one there. And I want to do one more. What happens if you get this kind of a derivative, or this kind of function, where, so we can sneak this in here. The original function is increasing to a flat spot, then it continues to increase, and then does this. The piano top, if you remember doing those. Okay, so there's our x-axis, and so we go to do the same thing. Well, this is when we go to do our derivative here. You go to your peak, that's no problem, but you want to remember the flat spot. Slope of my tangent would be 0 there, so I have an x-intercept, but I have a slope of the tangents there. It's not a peak or a valley, it's a flat spot. Still needs a handcuff, okay? So now we ask ourselves, what, from negative infinity here, or you just say from the edge of the graph here, the original function is increasing. I want to make sure to label that in black there. That's f prime. Or sorry, it's f, okay? The original function in black here is increasing the entire time, except it pauses right there, which tells me the graph of the derivative needs to be positive. But it's 0 right there. So I'm above the x-axis, but I come down to this 0, but I never go negative. I just kiss right there, and I continue to increase, but then I have to get back down to here. So you always want to remember, kisses make flat spots. Always, 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 always. Okay? Now, the original function's decreasing. I'm just negative, and there's f prime. Okay? Now, piano tops are typically 4th degree functions, so its derivative looks 3rd degree here. And then we would go to our second derivative. So we go to peaks, valleys, and flat spots of red. We have that handcuff there, and then this handcuff's right on top of each other. Okay? So what is red doing? Red is decreasing. Therefore, the graph of the derivative is negative. Red is increasing. Graph of the derivative is positive, but I got to get back down to 0. Graph of the derivative is negative, or is decreasing. So the red is decreasing. Graph of the second derivative is below the x-axis, or negative, and there's that. And again, if I did this right, these x-intercepts should correspond to inflection points on the original, which they do. Okay, so you want to have this always available to refer to, and now we're going to go back to the question, because the question asks this. It says, on what interval is the graph of f both increasing, or g it says, g is both increasing and concave down. Well, let's just get the increasing taken care of. Okay, so let's look at this graph here. When was f increasing? F was increasing whenever the derivative was above the x-axis, or positive. So when red is above the x-axis, the original function was increasing. When red was below the x-axis, the original function was decreasing. So this says, where's the original function increasing? Well, it's not here. It's only increasing from -5, or it's only positive from -5 to 2, so it could be there. So what I'm going to do is just write, I'm going to put my candidates here. So I'm going to actually do this. Some students like to do this. We'll go -5, right? And we'll go -4, -3, -2, -1, 0, 1, 2, 3, and then we're at 4. So let's see where it was not. So red was below the x-axis from positive 2 to 4. So it's not here. This is out. Okay. The rest of it, it could be there. So now let's read the second part of it. It says, on what open intervals is the graph both increasing, got that, and concave down? Well, now let's go back over to here. Look at where this original function is concave down. It was concave down when the first derivative was decreasing. First derivative is decreasing, original function concave down. Original function, let me say it again. Original function concave down, f prime, is decreasing. So the red function, the derivative, is decreasing. Original function is concave down. F prime, derivative, is increasing. Original function is concave up. So all we have to look for is, where is the red function here? Where is it decreasing? That'll tell us where it was concave down. Well, it's decreasing from -5 to -3. So it could be here. All right, it's increasing from -3 to 0, so it's not here. No good. And we are decreasing again from 0 all the way to 4, but this was already thrown out, so it looks like we're here. So it looks like those are the two spots where we have the first derivative is doing two things. The first derivative is positive, but it's also decreasing. Okay, so let's pretend the question applied to this graph right here. Where on this graph right here is the original function both increasing and concave down? Where is it increasing and concave down? Well, here's the only spot it's concave down, and it was only increasing to this first part right here. So what's red doing in that spot? Red is above the x-axis, and it's decreasing. Above the x-axis and decreasing. So from -5 to -3, it's above the x-axis and decreasing. Between 0 and 2, it's above the x-axis and decreasing. So those are my two intervals. So I'm going to say the graph of G is increasing and concave down -5 less than x less than -3, and what's our other one? 0 less than x less than 2. The graph of x is increasing on those intervals, then we have to explain why. Because the derivative, f, which is equal to g prime, is positive, and it was also increasing. Those were the two conditions. Okay? So you just want to take your time with that one and make sure you have this graph available so that you can compare your work. You always want to have this here. Okay, let's look at part C. Part C says the function h. So here we have a little bit of function build, kind of from potpourri or function build styles. And so they tell us here that h of x is equal to g of x divided by 5x. Okay, function h is defined by that, and they want you to find h prime of 3. Okay, so they want h prime of 3 equals what? Well, it's a derivative question combined with, do you know your quotient rule? So let's see what we get here. H prime of x. If we remember our quotient rule, derivative of the top, that'll be g prime of x times the bottom, 5x, minus the top, g of x, times the derivative of the bottom, which would just be 5, all over the bottom squared. So that would be 25x squared. I'm just going to square it. Okay. There's our derivative. Now we have to evaluate it at 3. So let's see what we get here. H prime of 3 is equal to g prime of 3 times 15 minus g of 3 times 5 all over 3 squared is 9. 9 times 25, that's 225. Okay. Now, let's see, what else do we got here? We should have enough information here, so what do we have here? H, or g prime of 3. Well, g prime of 3, this is g prime, so g prime at 3, we'd figured that out before, is a -2. So it looks like I got -2 times 15 minus g of 3. Now, is there anywhere on the problem we knew g of 3? That was actually part A. G of 3 is 9 times 5. And then we're still all over 225. Okay, so it looks like we get -30 minus 45 all over 225. That's negative 75 over 225. And I believe 25 goes into both of those. So that would be negative 3. And this will get us back to the 9 we had before. And one more time, we'll do negative 1/3. There it is. So I guess we could put that right here, negative 1/3. Okay, there is C. All right, now it's time for part D. So I'm going to erase our work here from our number line. Okay, draw a line here. And let's see what we can figure out here. So part D says function p is defined by, so now they give us a new function. So p of x is defined by f of x squared minus x. Okay? Find the slope of the line tangent to the graph. Slope of a tangent, slope of a tangent, slope of a tangent. Translation, find the derivative. So find p prime of x. That's what we need, because that's slope of a tangent is a derivative. So we need to do f prime of x squared minus x, but we've got to chain rule this, so I have to multiply that by 2x minus 1. Okay? So it says find the slope of the line tangent to p at the point where x is negative 1. So they do give us the x value. So it's p prime of negative 1 is equal to f prime of, let's put negative 1 in here. Negative 1 squared is 1 minus minus 1. So this becomes f prime of 2 times, put in negative 1 here, we get negative 2 minus 1, we get negative 3. Okay? So now we need the derivative. We need f prime at 2. Well, if this is the graph of f, we need f prime at 2. That would be the derivative at 2. So let's see what's going on. So f prime at 2, if you'll notice this line right here, and they love to do this on these graphs. Remember, the slope of a tangent, if the function is linear, is just the slope of the line. Tangents to a linear function are the line itself. So the derivative of f, if f is linear, is just the slope of the line. Well, we had actually calculated this earlier. You could do it many places, but the slope of this line is 2, or negative 2. We did that earlier in the problem. Okay, so that's going to be negative 2. So that's negative 2, and then times negative 3. Looks like our derivative at negative 1 is equal to 6. Okay. And there it is. So what did we have? They gave us a derivative graph. And we didn't do too much here with maxes and mins. It was just about the only part there they focused on increasing and concave down. So we still had to read this, but there was no maxes or mins on this one. But we did have to use an aspect of the fundamental theorem, area under a curve. And then we had a kind of a crossed over here with some function build and just reading a graph. Okay? So there it is, 2014, question number 3. Thanks for watching. We will see you next time.